There are lots of circumstances where we're working backwards compared to what we did in the previous lesson, where we have a line or we have some sort of real-life situation and we want to model it using a linear function, a linear equation of some sort. So before we get to kind of an application type circumstance, I want to take a look at a couple of examples where it's just a graph that we want to write an equation for, and we're going to do that using our slope-intercept form. We could eventually convert it to standard form if we wanted to. We could write it in point-slope form from the very beginning if we wanted to. We're going to go ahead and stick with slope-intercept form to keep life easy. So in the slope-intercept form, y equals mx plus b, the two things that we need to know are the slope of the line, and we need to know the y-intercept. If we know those two things, we just slot those into m and b in our equation, and we've got it for that particular line. So to start off with, I think the easiest thing to identify is the y-intercept, because we're literally just looking for the place where our graph is crossing through the y-axis. And so we're just looking for a single number there, and so hopefully we can tell that that number in this case where we cross through the y-axis is 1. So then from there, we've got to figure out what the slope is. And so that's where this point here is going to help us out, because we're going to measure the rise and run from the point, the y-intercept that we have there, to that second point. So I'll just change colors here to kind of give us a little contrast. So this vertical rise to get from the height of the first point to the second point is 1. So our rise in this case is 1. And then our horizontal movement, if we just count that along the x-axis, 1, 2, 3, 4, so we have a run of 4. So that's our slope there. We have a rise of 1, a run of 4. So we can write our equation as y equals, just slot those numbers in, 1/4 x plus 1. You may want to try the second example before continuing on with the video, but again, we're working with y equals mx plus b, so we just have to identify those two features. So our y-intercept is going to be right here, so that means b equals 2. And then for the slope this time, we're going down to get from the first point to the second, so we can count that down 1, 2, 3. So our rise is -3. Our run, again, is going to be 1, 2, 3, 4. We're moving 4 units from the y-axis to get to that point, and that's going to be positive. So that means our slope is going to be -3/4. And so now we've got the two features that we need. So we go y equals -3/4 x plus 2. So we just need to identify the y-intercept, identify the slope, plug those two things into our equation for m and for b, and then we've got our equation given a line. And so the situation doesn't change in any meaningful sense when we've got more stuff going on in the problem. So here we just have a bunch of context surrounding the graph, but we still just have a straight line for which we have to find the slope and we have to find the y-intercept. And then once we have that equation, we can go ahead and make some interpretations of what that equation represents. But the bottom line is, for the equation, we're going to do the same thing we did on the previous examples. So in this case, it says the graph shows that the distance y, so y is the distance that an asteroid travels in a period of x seconds. So the x-axis is keeping track of the time, and the y-axis is keeping track of the distance. So we're going to do the same thing. Y-intercept, I'll start there just because that's the easy thing to identify. So in this case, we're passing through the origin, so our y-intercept is 0, so that's simple. And then for the slope, we just have to figure out what is our rise and what is our run. Well, our vertical distance from the origin to get to the point right here that we're going to use is just that y coordinate, so that's going to be 24. And then our run, that horizontal distance that we're traveling, is going to be 5 units. And so you'll notice that on this graph, we have the x and y axes scaled differently. So we're counting by ones along the x-axis, 1, 2, 3, 4, and so on. But we're counting by fours along the y-axis. And so that just is something that we do from time to time when the scale makes sense for us. To scale differently makes sense for us. So slope then, rise over run. So our vertical movement is 24, and our horizontal movement, the run, is 5. So to write our equation, again, if we see it in front of us here, y equals mx plus b. So we've got y equals 24/5 x, and then we could put a plus 0 if we wanted to, but that there is good enough for us. So now that we have the equation, we want to make sure that we understand what that equation represents, what does the slope represent, etc. So slope's the first thing we're going to focus on. And in this problem, it probably makes sense, even though for graphing purposes we typically want to leave our slope in fraction form, we probably should convert this 24/5 to a decimal. Makes more sense for the context of this problem, as we'll see going forward. So if we push buttons on our calculator and if we divide 24 by 5, we're going to get 4.8. So instead of 24/5 times x, we've got 4.8 times x. So what does that slope represent? Well, remember, to get that 4.8, to get that 24/5, we are taking the y movement, which was measured in miles, and dividing it by the horizontal movement, which is keeping track of seconds. And so really what the slope represents is the number of miles per second that our asteroid travels. So then we're asked to figure out how far this asteroid travels in 1 minute. So again, in our equation here, remember that x is keeping track of time and the y is keeping track of the distance. So if I want to know how far the asteroid is going to travel in 1 minute, I'm going to replace the x variable with 1 minute, but please note that we're keeping track of time in seconds, so I'm not going to plug in 1 in place of x to represent that 1 minute. I need to convert that minute into seconds. I have to make sure that my units match up, otherwise I'm mixing apples and oranges when it comes to my slope being measured in miles per second and my time being in minutes. So I need to convert that to 60 seconds. So I'm going to plug that in. So I've got 4.8 times 60. So if I multiply that out on a calculator, I get 288 miles. And then in the second question, it asks how long does it take for the asteroid to travel 720 miles. So this time I know the distance and I'm trying to figure out the time, so I'm going to plug that 720 in for y. And then I'll still have 4.8x. And so now I can scroll here a little bit. I've got to solve for x, so I'm going to divide both sides by 4.8. And so we get a time of 150. So now again, we want to make sure that we label our answer to get the correct context. And so once again, I'll point out, remember that x is being measured in seconds, so that's 150 seconds. So we can write our answer that way, or if we were inclined to and we wanted to convert that into minutes, we could divide that answer by 60, and so then we could also report our answer as 150 divided by 60, which is going to be 2.5 minutes. So either of these results to report our answer will do.